everyone, let's dive right into this explainer. When we think about the electric vehicle transition, we usually just picture, well, the car itself, swapping a gas pump for a plug, right? But the reality? It's so much bigger than that. We are literally looking at a complete rewiring of our infrastructure, our roads, and the entire national power grid. To truly wrap our heads around this revolution, we need to take an ecosystem approach. Here's a quick look at our agenda. We'll start with the EV boom, then zoom in on solid-state batteries, check out wireless charging roads, look at the macro power grid, discuss planning for the load, and wrap up with our symbiotic energy future. All right, kicking things off with Section 1, the electric vehicle boom, and the massive scale of this transition. To put a real number on this, 42 million. The U.S. Department of Energy is projecting a high adoption scenario of 42 million light-duty electric vehicles on the road by the year 2030. 42 million. I mean, that is just a staggering leap. And keep in mind, that's just passenger cars. Medium and heavy-duty electric trucks are also projected to see absolutely massive growth as major commercial delivery fleets make the push towards zero emissions. Now notice how the spatial density of these vehicles clusters heavily in urban areas. That's exactly where the demand for power is going to spike. If you look at those deep blue circles concentrated on the coasts and in major cities, the Department of Energy actually projects that up to 35% of light-duty vehicles in these urban cores could be electric by 2030. Compare that to maybe 3% in rural areas. So what's the takeaway here? Well, this uneven distribution means that while our national grid absolutely has to adapt, the real gritty stress tests are going to happen locally, literally neighborhood by neighborhood. Moving right along to Section 2, solid-state batteries and how we are solving range anxiety. Okay, so what exactly is this? At its core, a solid-state battery is a technology that replaces the liquid or polymer gel electrolytes found in your traditional lithium-ion batteries with a solid conductive material. And why does that matter to us? Well, automakers all over the globe are actively shifting from lab test to real-world pilot production of these things, with the goal of mass commercialization somewhere between 2027 and 2030. This isn't just a minor tweak, it's a fundamental chemistry shift that unlocks entirely new capabilities. The contrast here is pretty striking. Your traditional lithium-ion batteries rely on liquid electrolytes. That means lower energy density and traditional charging speeds, and right now they cost around $105.40 per kilowatt hour. But on the flip side, solid-state batteries use solid electrolytes. We're talking high energy density, much faster charging, and way improved safety. Seriously, these things can deliver extreme ranges, like up to 1,000 kilometers on a single charge, and boast rapid 400 kilowatt charging capabilities. But there's a catch. Their current manufacturing cost is sitting at $158.80 per kilowatt hour. That price tag remains a huge bottleneck that the industry has to overcome before they become the new standard. Let's zoom out a bit for Section 3, wireless charging roads, because the infrastructure outside the car is evolving too. Check this out. In Detroit, which is of course the historic birthplace of the American automobile, an 18-month project successfully created North America's first public wireless EV charging road, right there on 14th Street. This project used inductive coils embedded beneath a quarter-mile of asphalt. They had this Ford E-Transit shuttle, affectionately nicknamed Ellie, fitted with a wireless receiver. And guess what? It successfully charged while it was moving and while it was just stopped in everyday urban traffic. It even powered through winter storms and summer heat. Think about what happens when this technology seamlessly integrates into our roadways. Vehicles could achieve essentially endless range. By embedding charging infrastructure directly into the street, commercial vans and public transit buses can operate with much smaller, lighter batteries simply because they're constantly topping up on the go. Plus, it spreads out the energy demand over time and space. That makes it an incredibly smart solution for urban fleets, completely avoiding that massive grid strain of having every single vehicle plug in at a depot all at the exact same time. Which brings us to Section 4, the power grid, and figuring out how we're actually handling the load. So the absolutely crucial point here is recognizing the sheer intensity of high-level charging. While level 1 or level 2 charging at your house has a relatively minor household impact, stepping up to a single DC fast charging station with just 4 ports demands 0.6 megawatts of power. Now brace yourself for this. A large commercial truck stop built to handle heavy-duty electric trucks demands nearly 20 megawatts. 20 megawatts. That is a staggering concentration of load, and it completely rewrites the engineering requirements for the local distribution grid. And that leads perfectly into Section 5, Planning for the Load, where we look at adapting forecast models. Historically, grid planning was pretty deterministic. It was based on highly predictable historical trends. But today, instead of those predictable trends, utility planners have to account for multiple overlapping variables. We're talking geographic location, the time of charging, weather conditions, different vehicle types, varying battery capacities, and above all else, unpredictable consumer behavior. It's now a stochastic, behaviorally driven system. Millions of independent customers are just deciding on the fly when and where to plug in. Finally, let's wrap up with Section 6, a symbiotic energy future. Spoiler alert, the grid isn't doomed. The U.S. Department of Energy highlights a really fascinating perspective here. They state that EVs' relationship to the grid can be a symbiotic one because they offer flexibility in the time and location where they use energy, and they store energy in the vehicle battery that could be used for non-transportation applications. Think about it. Because cars sit idle for long periods of time, they aren't just a drain on the grid. They actually have the potential to act as massive distributed mobile batteries. So an electric vehicle isn't just pulling power, it's communicating with the grid. Through smart utility rates, those wireless charging roads we talked about, and advanced solid-state storage, these vehicles can absorb excess renewable energy, like wind and solar, when it's super plentiful. And crucially, through bidirectional charging, they can discharge power back to stabilize the grid during peak hours. What begins as just a shift in how we get around evolves into a fully integrated, incredibly flexible energy web. To conclude our explainer today, I want to leave you with this question. How will your own daily commute act as a mobile power plant in tomorrow's synchronized energy web? The EV revolution isn't just about changing what you drive. It's literally about changing how we power our entire world. Your vehicle might one day power not just your journey, but your home and your entire community. Thanks for joining me, and keep exploring.